On our previous lectures, we have learned mechanics, and now we are beginning a new topic. Electrostatic field. Electrostatic field is a field that is produced by a system of fixed electric charges. And it is necessary to remind that electric charge may be written as this. It may be represented as sum some elementary charges multiplied by n, where n is integer number, and this value E, elementary charge, is equal to 1 602 176 multiplied by 10 to the power of minus 19 and multiplied by minus 19 coulombs. Coulomb is a unit for electric charge. Coulomb is unit for electric charge. It is named by scientists who discovered a law of electrostatic interaction. Coulomb. This is a unit for electric charge, and the name of scientist who discovered law of electrostatic interaction. We will learn it in a few minutes. Electric charge. Every electric charge may be represented by this formula. Where E is elementary charge. And what is necessary to say? In a closed system, electric charge is constant. Closed system is a system that cannot change with its environment. That cannot change electric charges with its environment. It is closed system, and in closed system, electric charge is constant. This fact is known as law of conservation of electric charge. And as you can remember, charges with same sign charges with same sign repel from each other, and charges with different signs, plus and minus, attract to each other. And the question is how to define this interaction, how to find force of this interaction. And the answer was given by Charles Coulomb, by this scientist, and it is known as Coulomb's law. It is known as Coulomb's law. Coulomb's law. So let's draw a picture to understand this law. Imagine that we have two point charges. We have 2 point charges with radius vectors r and r1. For example, r1. Here we have charge q1, and here charge q. Here charge q. Here charge q. Here we have charge q, and we can also connect them with vector delta r, and here r. And according to Coulomb's law of electrostatic interaction, we can write that force of electrostatic interaction is equal to 1 divided by 4p epsilon 0, 1 divided by 4p epsilon 0, q and q1, divided by delta r to the power of 3, delta r vector, and this may be written. This may be written in some another form. 1 divided by 4p epsilon 0, 4p epsilon 0, q and q1, absolute value of vectors r minus r1 to the power of 3, and multiplied by r minus r1. This is a force of electrostatic interaction. And we can also sometimes we can also use its absolute value, but Before this, it is necessary to write this force on picture. So here F is force that impressed on charge Q. So this is a force that produced by electrostatic field of charge Q1, and it means force impressed on charge Q. So this is force. This is force. With this force, charge Q1 acts on charge Q. Acts on charge Q. If we want to know force impressed on charge Q1, we have to change places. We have to change places of vectors r and r1, and we will get force impressed on charge Q1. And according to the third Newton's law of motion, its absolute value will be equal to absolute value of force F, but the direction will be opposite to the direction of force F. Okay, absolute value of force F. Absolute value of force F, according to the formula above, will be equal to this, but it is necessary to change power from 3 to 2, and here will be the same situation. We have second power. We have second power. Okay, and what about epsilon zero? Epsilon zero is electric constant. Epsilon zero is equal to 8.85 multiplied by 10 to the power of minus 12 farads divided by meters. And it is the same as 8.85 multiplied by 10 to the power of minus 12 in squared meters. Squared meters, not squared meters, in squared coulombs. Squared coulombs divided by newtons multiplied by squared meters. Yes, this will be correct. This will be correct. And this is electric constant. I'll write that it is electric constant. Electric constant, or what is the same, vacuum permittivity. Or vacuum permittivity, or or permittivity of free space. Permittivity of free space, or permittivity of free space. So these names are the same. These names are the same. Or permittivity of free space. This is Coulomb's law. This is Coulomb's law. Okay, do you have any questions about this?
So far, so good. Same.
Okay. Okay, if it is good. And let's consider a system of electric charges, Q1, Q2, Q3, that act on charge Q. That act on charge Q. According to Coulomb's law, force impressed on charge Q will be equal to sum of forces F I, and this is equal to I'll just copy this. I'll just copy this here. I equal to 1, from 1 to n, and here I will have sum, but it is necessary to replace 1 with I. To replace 1 with I. Okay, and what can we see? Charge Q and 1 divided by 4p epsilon 0 may be written outside of the brackets, outside of the sum. So we can write Q divided by 4p epsilon 0, Q divided by 4p epsilon 0, and it is necessary to change 1 by E, 1 by I, lower index I. Sum I equal 1 from 1 to n, and qi divided by r minus r1, or no 1, it will be I, of course. Of course, it will be I to the power of 3, and multiplied by r minus ri. And as you can see, we can divide left and right sides of this equation. Divide left and right sides of this equation by Q, by charge Q, and we will obtain F divided by Q. F divided by Q is equal is equal to this, is equal to this. But it's necessary to replace Q with 1. So we have divided left and right sides by charge Q. And as you can see, this right side of the equation doesn't contain charge Q. And it means that this right side doesn't depend on charge Q. And if the right side doesn't depend on charge Q, the left side doesn't depend on charge Q either. So it means that this value doesn't depend on charge Q. So if we, for example, if we increase Q 2 times, absolute value of F will also increase 2 times. But their relation F divided by Q doesn't depend on charge Q. And this fact allows us to define a new value that is known as electrostatic field intensity. Electrostatic field intensity. This is electrostatic field intensity. Electrostatic field intensity. Electrostatic field intensity. Electrostatic field intensity. Maybe here electrostatic field intensity. Electrostatic field intensity. Electrostatic field intensity. And if you know electrostatic field intensity, we can easily calculate force impressed on charge Q. That is placed into this electrostatic field. From here, we just have that force of electrostatic interaction may be simply calculated by this formula. Charge Q multiplied by electrostatic field intensity. And this is useful. This is useful in practice. And the question is just how to calculate electrostatic field intensity. Sometimes it may be quite difficult. But from this formula, we can see that only if we have only one charge Qi, the electrostatic field intensity will be some EI, and it is equal to 1 divided by 4 P epsilon 0, 1 divided by 4 P epsilon 0, and multiplied by this. And from comparing, and if we compare these two formula, we can notice from comparing these two formula, that electrostatic field intensity of system of electric charges may be written as a sum of electrostatic field intensities E1 plus E2 plus, in the same way, En, and if we write this in short way, E is equal to 1, E is equal to N. Electrostatic field intensity of charge with number I. And this formula is known as superposition principle. Superposition principle. Superposition principle. Superposition principle for electrostatic field intensity. For electrostatic field intensity. For electrostatic field intensity. For electrostatic field intensity. Okay, do you have any questions?
So far, so it's okay.
Okay. Okay. So I will remove this. I'll remove this, and I will remove this. I will remove this. And as you remember from mechanics, if we have a field of some central force, this field is always a potential field. This field is always a potential field, and we know that central force means that this force depends only on distance to some center. In this case, this distance is equal to absolute value of delta R. So electrostatic field is a field of central force. So it means that this is potential field. And from mechanics, we know that work of force of potential field, this work may be written, not work. I will for potential field we can define potential energy. For every potential field we can define potential energy, and we will write this as double V. In mechanics, as you can remember, we have used U. We have used this letter, but we cannot use this for electromagnetism because here it is necessary to sign potential difference, as we will learn later. So potential energy, according to the definition, is equal to minus in linear integral from R0 to R, force F, dr, and plus some initial potential energy. W0 is a potential energy in point that defined by radius vector r0. We can define r0 and w0 as we want to define. We can define this in any way. Okay, and let's divide left and right sides of this formula. Let's divide left and right sides of this formula by charge q. Let's divide this by charge q, left and right sides. We will get W divided by q. W divided by q is equal to minus linear integral from r0 to r f divided by q, f divided by q, dr plus w0 divided by q. And what do we have? We know that force impressed on charge q divided by this charge is equal to electrostatic field intensity. So this is electrostatic field intensity. Okay, and what about potential energy divided by charge? Potential energy of charge q divided by this charge. And for this relation, we can define new physical value that is known as electrostatic potential. P is equal to W divided by Q. And according to this definition, W divided by Q is equal to phi, and W0 divided by Q is equal to some phi 0. So from this, we obtain the definition of electrostatic potential. Is from R0 to R, from R0 to R, electric field intensity dr, and plus phi 0, and plus phi 0, plus phi 0. So this is electrostatic field, electrostatic potential. This is electrostatic potential. So we can write this here: electrostatic potential. Electrostatic potential. And electrostatic potential. Electrostatic potential can be defined by this formula, and this is connection of electrostatic potential and electrostatic field intensity, and of course, potential energy of charge q in electrostatic field. So potential energy of charge q in electrostatic field potential energy of charge q in electrostatic field may be defined by a formula of charge q in electrostatic field is W is equal to q multiplied by potential phi. So we have simple formula to find potential energy. Of course, if we know electrostatic potential. Okay, I think there is no questions. So let's say some other facts. Let's consider some other facts. As you know, also from mechanics, force may be derived from potential energy. According to the formula, F is equal to minus gradient of potential energy. And if we divide left and right sides by charge q, if we divide, it will be minus gradient of W divided by Q. And if we use this definition of electrostatic field intensity and definition of electrostatic potential, W divided by Q is equal to phi, we will get that electrostatic field intensity is equal to minus gradient of electrostatic field electrostatic potential. So this formula allows us to define electrostatic field intensity if we know electrostatic potential. So this formula and this is are almost the same, but first formula allows us to find the electrostatic potential from electrostatic field intensity, and the second formula allows to find electrostatic field intensity from electrostatic potential phi. potential phi. And it is necessary to say that units for electrostatic potential are volts, and it can be marked as V, volt unit for potential, and units for electrostatic field intensity are volts divided by meters. Volts divided by meters are units for electrostatic field intensity. Okay, and as we also know from mechanics, work of conservative force, work of force of potential field may be defined as for point that moved from place 1 to place 2. It may be defined as integral from R1 to R2 f dr, and it can also be written as minus potential energy in point R2 minus potential energy in point R1. And if we open brackets, we will have potential energy in point R1 minus potential energy in point R2. Okay, and let's remember that force may be written as product of charge Q and electrostatic field intensity, and potential energy may be written as product of charge Q and electrostatic potential. So from here we can write that work of force of electrostatic interaction can always be written as charge Q multiplied by linear integral from R1 to R2 electrostatic field intensity dr, and this will be equal to Q multiplied by phi in point R1 minus phi in point R2. And here we have difference of potential or potential difference, and this potential difference often is often written as letter U. As letter U. So here we have U. U is equal to this integral. U is equal to this integral, or this is equal to phi in place R1 minus phi in place R2. In place R2. So this value is potential. This value is potential difference. Is potential difference. Potential difference or voltage. Potential difference or voltage. Potential difference or voltage. And this formula allows us to define work of electrostatic force or work of electrostatic forces. Work of electrostatic forces. Work of electrostatic forces. Work of electrostatic forces may be defined by this formula. May be defined by this formula. Okay, and what will happen? What will happen if we have motion along the closed trajectory? Along the closed trajectory. In this case, closed trajectory begin of this trajectory is the same as end of this trajectory. So in this case, R1 is equal to R2, and of course it means that phi in a point R1 minus phi in point R2 is equal to 0. And from here we have that. Linear integral along the closed trajectory. It may be written as integral with this circle. It is linear integral along the closed trajectory. So from here and here we have that this integral is always equal to 0. This is always equal to 0. So for electrostatic field, we have formula. And maybe you can remember from calculus that if this equation is true, then field is potential. Field. If this equation is true, and we can see that we have this for electrostatic field. And because electrostatic field is a kind of potential field. Electrostatic field is a kind of potential field. Or what can we what else can we say about electrostatic field? We can notice that electrostatic field intensity, according to this, can be written as sum of electrostatic field intensities, and from this it means that electrostatic potential can be written as phi 1 plus phi 2 plus some phi n, and this is the same as sum I is equal to 1, I is equal from 1 to n, and phi I. And this formula is known as a superposition principle for electrostatic potential. Superposition principle for electrostatic potential. For electrostatic potential. For electrostatic potential. For electrostatic potential can be written with such formula. Okay, do you have any questions? Do you have any questions about
Electrostatic? No.
no. Yeah, so we to define electrostatic field, we have two values. Electrostatic field intensity and electrostatic potential. And of course, electrostatic potential is more convenient to use because this value is scalar. And electrostatic field intensity is a vector. This is vector value. Of course, it is more convenient to work with scalars than with vectors. So if it is possible, we should always define electrostatic potential and work with it, and work with it. So according to this formula, for example, for point charge, we can write that that electrostatic field intensity of one point charge is equal to 1 divided by 4 p epsilon 0, and divided by 4 p epsilon 0, and here we have qi divided by r minus ri and to the power of 3. denominator is to the power of 3, and here in numerator we have r minus ri. It is electrostatic field intensity of one point charge qi. Okay, and what about electrostatic potential? What about electrostatic potential? Let's try to find this for point charge. Let's try to find this for point charge. According to the definition, phi is equal to minus linear integral from r0 to r, electrostatic field intensity delta r plus phi 0. And as it was said before, we can choose any value of r0 and phi 0. And it is useful. To choose. Next values. It is useful to choose r0. R0 tends to infinity. R0 tends to infinity, and phi 0 is equal to 0. In this way, we will have the simplest formula for electrostatic potential of point charge, and it is the most common choice. But it will doesn't work in only one case. When we have a system of electric charges in unlimited part of space. If part of space with electric charges is unlimited, this integral will be equal to infinity. So in this case, it will be impossible to choose this. But for point charge, or for system of charges in limited part of space, it is always possible. And in this case, it is often the best choice. So we will get minus integral from infinity to r, e dr, or what is the same? It will be integral from r to infinity. From r to infinity, e dr. And of course, if we have this, we will get qi divided by 4p epsilon 0, 4p epsilon 0, linear integral from R to infinity. To infinity, now we use this formula from infinity, and R vector minus Ri divided R minus Ri to the power of 3, and dr and dr. Okay, and how to calculate this linear integral? How to calculate this? We know that electrostatic field is potential. Electrostatic field is potential, and it means that this linear integral depends only on initial and final position. Depends only on initial and final positions, and doesn't depend on paths from R1 to R2. So it means that we can choose any path as we want to. And let's choose this to meet the next condition. E has the same direction as dr. We can choose any path, and let's choose path that meets condition of that means this condition. And according to this formula, electric field intensity vector E has the same direction as this vector. So from here we have that it is the same as R minus Ri. And if two vectors have the same directions, we can write that their scalar product is equal to absolute value of R minus Ri. This absolute value multiplied by multiplied by absolute value, of course, absolute value by, of this vector, and multiplied by cosine 0. If two vectors have the same directions, the angle between them is equal to 0. And we have from here that this scalar product is equal to absolute value of this difference multiplied by dr without vector. So this result means that we can significantly simplify this linear integral. So we can simplify this to simple integral. We can simplify this to just defined integral, from r to infinity, Here we have this. In numerator we have this, and in denominator we have this in denominator. And after simplifying, we have that integral from r to infinity, dr, and divided by this modulus of difference of vectors r and ri to the power of 2. Okay, and the question is how to calculate this integral. I think to do this, it will be useful to change differential. So we will get d. And absolute value, differential of this absolute value, and divided by this absolute value to the power of 2. And if we change differential, we have to also change integral limits. Of course, I think a lower limit will be some r, absolute value of r minus ri, and the upper limit will still be infinity. So we have obtained improper integral, and to calculate this, it is necessary to rewrite it in some another way. Limit alpha tends to infinity, and here we have this integral, but upper limit will be alpha instead of infinity. And this integral may be easily calculated. As you remember table of integrals, dx divided by x to the power of 2. This is minus 1 divided by x plus c. So we can use this here. We can use this here, and we will get we will get limit alpha tends to infinity. Alpha tends to infinity minus 1 divided by this absolute value, 1 divided by this, and here this is equal to lower integral limit, and here this is equal to upper integral limit alpha, from this to alpha. So we have limit alpha tends to infinity. Limit alpha tends to infinity. Open round bracket. Open round bracket minus. Open bracket again. First term will be 1 divided by alpha. 1 divided by alpha minus 1 divided by absolute value of vector r minus vector ri. Minus vector ri. And let's open inner brackets. Let's open inner brackets. We will have open inner brackets to simplify this formula, and we will have 1 divided by absolute value, and minus 1 divided by alpha. And of course, if alpha tends to infinity, 1 divided by alpha, 1 divided by alpha tends to 0. And so we have obtained that it is equal to 1 divided by absolute value of r minus ri. Okay, do you have any questions?
Also, there's too many equations here, but yeah, after the example, it will be fine.
Yes, it is quite difficult because a lot of formula, a lot of formula and improper integral we have here, but according to our actions, we have got that this improper integral is equal to this fraction. Oh, it was the most difficult step here. It was the most difficult step, and now I can remove. Now I can remove this, but it will be easier on practice, because on practice we will just use we'll just use some ready formula to calculate electrostatic potentials and electrostatic field intensities. So what do we have? We have that electrostatic potential of point charge is equal to 1 divided by 4p epsilon 0. 1 divided by 4p epsilon 0 q I divided by absolute value of r minus r I. R minus Ri. So this is a formula for electrostatic potential of point charge. And we can make some summary. We can make some summary and make some conclusions that electrostatic field field intensity and electrostatic static potential in that is produced in some point r by electric charge q placed in point Ri. So electrostatic field intensity and electrostatic potential that is produced in point R by electric charge Qi, electric charge Qi in point Ri. So electrostatic field intensity. Electrostatic field intensity is here, and electrostatic potential is here. Phi is equal to 1 divided by 4p epsilon 0 1 divided by 4p epsilon 0 Qi divided by absolute value of r minus Ri. But of course, it is necessary to notice that this is true if we meet these conditions. If R0 tends to infinity and phi0 is equal to 0. In these conditions, this is true. Of course, it's necessary to notice if R0 tends to infinity and phi0 is equal to 0. Without these conditions, with another conditions, we will have another formula for electrostatic potential. But this is the most often used this formula. Okay, what questions do you have? No questions.
No, I don't have.
Okay. Okay, and the last thing for today will be one more value that is known as flow. That is known of flow of electric field intensity. Flow of electric field intensity. This value can be defined by the integral, and this value is known as electric flux. Electric flux. Electric flux. Electric flux. It is according to the definition. It may be marked as Fe. Fe, and it will be surface integral. Surface integral of E electric field intensity ds. And this is electric flux. And we will talk about this more particularly in the next week. We will talk this more particularly next week. And I think this is enough for today. Maybe you have some questions.
Nope.
No, okay, that's great. That's great. So thank you for your attention, and I hope to meet you next week.
See you, teacher. Have a nice day. Have a nice week. Goodbye.
Okay, you too.